Frank.
There we go. All
Great.
right.
Yeah, we're going to put this on a YouTube webpage, and we have recordings for several other years there. I don't know. It's probably more exciting when you see yourself on in the program.
Yeah. Okay. So yeah, we're gonna in the future we're gonna try and start on time. Although, like I say, we hardly ever do. We start, by 7:02 or 7:04 or 7:05, something like that. Um, and let me tell you that as we go along, we're going to be covering all the chapters and going over lots and lots of the test questions. But still, you do best when you actually read the chapters yourself. You also do best when you take the online tests. There are a couple of sites, free sites, that will give you practice tests to take as we go through. We'll give you, as we go along, we'll give you the URLs to get to those things. One is on the ARRL website. The other is on a website that's called QRZ. There are several others, but those are a couple of good ones. Jerry actually has some that you can get to off of your iPhone if you are so inclined. At the moment, though, let me introduce our our instructor staff. I'm I'm Bob Lauer, N8REL, and I've been a
Nice to
ham
meet you.
since 2004, so about 18 years at this point. Got into it actually from an interest in shortwave radio, which I used to listen to a lot. Any rate, um, some the other guys are actually a lot more technical than I am. I do not have an engineering background. I don't have a heavy science background. I spent 48 years as an accountant, and so. But still, you don't need a heavy science background to get through this. Jerry, W9MPI. Jerry, do you want to talk? You want to tell a little about
Okay,
yourself?
okay. I'm a little embarrassed to say how long I've been in the hobby. Uh, I started off. I got my first license in 1957,
That
and
was a very good year. I remember it.
it sure was. Uh, well, I was a Boy Scout. I was trying to get my first class rank, and in order to do so, you had to know something about communications, either signaling with signal flags or Morse code or no, I don't know, drumming or something like that. Anyway, it took me about a year to learn the Morse code, and once I had it, I didn't want to get rid of it. So there were a bunch of kids in the junior high who were studying for their technician, not technician, novice. It was a very much lower class license, but you needed to send code for 5 words a minute. So I did that, learned the theory, and got on the air. Uh, okay, let's see. We've got Mike. Mike, you actually look even more extinguished than me. Go ahead, Mike.
I just realized I was muted.
Uh,
Evening all. Mike Slapinski, W2MJS is my call sign. Um, I've only been a ham for about probably like 8 years or so, but I've really only been a ham for about a year. I got my ham license because I'm also on the executive board and do a lot of volunteering for the city of Warren, where I live. And we do a lot of stuff for the city of Warren. And some of it takes a lot of people over a mile of distance closing off roads. And so the little public radios don't really do that. And so someone suggested, well, why don't we get our ham radio licenses and then we can talk over that distance? And so a bunch of us did. And I used it 2 or 3 times a year for 6 or 7 years until January when I really started getting into the hobby. And so my point in this is Bob has a path that he went down with his ham career, so to say. Jerry had another path that he went down with his ham career. And, you know, I have a third. We all have different reasons why. We all have different ways we're going to use our ham radio licenses. And so don't let anybody tell you what you should or shouldn't be doing. You know, how often you should use it or how often you shouldn't use it, or, you know, that's up to you. Whatever you want to do with this license, you know, you can do, whether you want to build radios, build antennas, or just buy stuff and talk on the radio and make friends. Whatever you want to do, you can do. So that's it for me.
Okay, thank you. All right, we're doing things a little different this time. You know, we used to do one chapter per night, but I decided this time, since chapter 1 is really a lot of fluff and doesn't have anything really you're going to be tested on, I'm just going to do a real back of the envelope summary of it, and then we're going to pass it on to Jerry, who will talk to you about chapter 2, which is the good stuff, radio waves and such. Throughout the course, we're going to be referring to ARRL, the American Radio Relay League. This is the oldest amateur radio association in the United States. It's been around for about 100 years. It has a presence in Washington. They provide educational materials, have free online tests, run a number of contests and things, and we'll be referring to them regularly. Now, amateur radio itself, it's a radio service. We are regulated by the Federal Communications Commission. Now, the Federal Communications Commission, let me see if I can do this. The Federal Communications Commission, of course, is a national government agency. Its chairperson at this time is a woman named, a very smart woman named Jessica Rosenworcel. She was actually appointed to the position in I think 2012 by former President Barack Obama. The chairperson position is a 5-year term. She was reappointed to the position by former President Donald Trump, and then reaffirmed, and she continues on through the Biden administration. Okay, smart lady. Now, one of the things that the FCC doesn't do at this point is they don't give the exams. They've delegated that authority to the amateur community itself. So the ARRL provides tests. It's one of the organizations that provides tests, and that's the one that we go through. Now, the test, I don't know if you caught that in chapter 1, but the test that you'll have is actually only 35 multiple choice questions, all multiple choice. Now, the 35 multiple, and there's lots of different tests because there's a question pool for the amateur license. The question pool is 412 questions, but you only get 35 of them, and you have to get 26 of them right. They cover, you know, a number of subjects. This is gives you an idea about what the last, I haven't updated this particular chart, but this shows you that you've got a certain number of questions about rules and procedures. You've got a couple of questions on radio practices. Electrical principles and components gets a bunch of questions. Modulation, which is radio waves, antenna feed lines, safety, those kind of things all get a few questions. You'll notice some of those areas are much easier than others, and we'll get you through that. And as Mike had said, and Mike is completely right, is that there's a lot of different aspects to amateur radio. You know, you may be interested in local communications. You may be interested in long distance communications to other hams across the world. Or as Mike, you may be part of a local emergency response team. That's one of the questions we asked you on the invite, is if you were a member of, you know, your local community emergency response team. A lot of people come in through that way. Other people just do it for technical challenges. All right. There's all kinds of ways you can bounce radio signals off the moon. reflect them off the aurora borealis, reflect radio signals off meteor scatter. That those kind of things take some talent and some practice. But there's also digital communications, video. You can actually send pictures over amateur radio, and then there's of course remote controlled craft, watercraft, model airplanes, and now of course the big thing now is drones that can be controlled through amateur radio frequencies. You can buy the little ones, the small drones, without an amateur radio license, but the power that you get to project, or that you get to send to your remote control device, is relatively limited. If you want a more sophisticated device and more distance, you need to get an amateur radio license. Just the technician license that you're getting, but that will allow you to send your radio signals to your drone or your model aircraft or whatever. I think I don't remember if it's limited to 1 watt or 5 watts, but still, for a kind of a toy drone without a license, you can get a couple hundred yards. But if you're using the amateur radio frequencies with your drone, you can get a distance of a few miles. So, is there anyone here that flies drones or model aircraft? Is that a reason for any of you to be getting into amateur radio?
I'm a Part 107 drone pilot, which is FAA licensed to.
Okay.
And I'm curious. I mean, I'm curious because right now a lot of the commercial drones, like you mentioned, the off-the-shelf, DJI is a popular brand. They're using Wi-Fi frequencies. They're using 2.4 and 5 gigahertz.
Oh, okay.
And you can go 5 miles easy with these days. But the catch is, the law says you still have to have line of sight of it. So these distances they claim really become kind of useless because you can't see a drone 5 miles away. But it's interesting to know we can use other frequencies, because there have been instances where I've flown where there's been a lot of interference on Wi-Fi channels. So being able to potentially build something that uses an alternate frequency is kind of intriguing.
Yeah, cool. Okay, that's kind of what you're gonna get out of Chapter 1, by the way. All of that, probably the only question that's going to come out of that could appear on your exam is knowing that the FCC regulates the amateur radio service along with others. Okay, let's get into the cool stuff, though. Jerry, are you ready to take over?
Well, I can talk a little more, and possibly people might have a few more questions. Why don't we field some questions first? Is one of the things that when we do classes and all that, we have a lot of people. We see some of their faces, some we don't. Sometimes we see people nodding, yes, 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 but are they really getting in there? So if you have a question, come on. Don't have to be shy with us.
All right. Hi, my name's Kurt, everybody. How you doing? I have a question that is probably too early for this, but as I prepare by studying and attending these classes, I think I should probably know the answer. I'm interested, ultimately, my use case is to use high frequency communications to communicate with family members that are in another part of the state. So I don't think I can use VHF or a tech, or there's a small part of the HF band, but I want to get a general license. Does it make sense for me to study both at the same time so that I'm cramming my brain full of all this information and try to test for both? Or does it make more sense to do the first, get some real experience, and then study for the next one?
You know what? You can do both at the same time. What you'll find is that studying for the general will reinforce what you're doing for the tech. The tech is much easier. Jerry has the greatest description of the technician license subject matter, and in that he says the subject matter, it's a mile wide but only 1 inch deep. So you're going to get you're going to go over the same subjects in the general, but you're going to go deeper and get more interesting stuff. The other thing is that do you know what a repeater is? Has anyone? Okay, because you know the repeaters, which hook by internet, hooked to other parts of the state. Now, I run the club's Sunday night 2-meter net. You know, it's the 2-meter band, VHF. But there are people that are calling in from Australia and Thailand because what they're doing is they're hitting their local repeater. Their local repeater is tied in through the internet to our repeater that's down in Oak Park on the top of a 12-story building, kind of at, let's say, Greenfield and
10 Mile.
12 Mile or 10 Mile.
10
Greenfield.
Mile, yeah.
Yeah, Greenfield and 10 Mile. Now that repeater hooks up to repeaters all over the world. So actually, what part of the state is your other family in?
He's in Presque Isle, so in the northeast tip of Michigan, and I'm in Oxford. So we're, it's like a 5-hour drive. So I'm
Yeah,
fairly
right.
confident that absent a repeater, if I wanted to literally communicate to the degree the atmosphere or whatever allows it, without any middle device, then I would
okay.
need something else, right?
Yeah, without going through the internet, without going through repeater, yes, you would need the general license. Well, the 10-meter band, you have privileges on the 10-meter band as a tech, and when conditions are right, I've contacted people in California, but the 10-meter band is real iffy, and it's sometimes yes and sometimes no. On the Sunday night 2-meter net, we do have a guy that calls in regularly from Bel Air, Michigan, the Central Lake Bel Air area. So that's getting up where, well, it's not as far up as Presque Isle, but near. Anyhow.
Okay, thank you.
Right, and sometimes the curvature of the Earth works against you. One of our friends, has a cabin in somewhere near Tawas City, and he can't do line of sight because the curvature of the Earth blocks him. So he has to use it's called Echolink. Well, there are a couple of systems they can use. Yeah, you're right. This internet type stuff is fine, but when things hit the fan, you can't depend on them.
Yeah, that's when your general license will come in
Right.
handy for long distance communications. Jerry, I'm going to go ahead and make you co-host.
Thank you. And do I have sharing privileges as well?
Yes, I believe.
Okay, good, very good. All right. Heavens to Betsy. Okay, if it's okay with you, Bob, I just want to amplify a little bit on certain things.
Oh, go right ahead.
So as far as introductory, a lot of you have probably gotten your mitts on this little device, a Baofeng. These are very, very cheap Chinese transceivers, and no, it's like a piece of Kleenex. If it breaks, throw it away. But it's a introductory piece. One of the things, if you buy it for different services, family radio services or whatever, you can't do anything with it. It has to be adjusted by someone with a first-class FCC license. But as an amateur, if you're brave enough, you can dip your soldering iron into this thing and do things to it, because that's what amateurs do, and that's what our license allows us to do. You've probably seen, bouncing signals off the moon, or well, in October, our club sponsored a flyover by the International Space Station with the Detroit Public Schools, and we had a dozen kids ask the astronaut questions in the 11 minutes that it took for the ISS to fly over. So these are some of the things we do. We have a Nobel Prize winner who develops digital signals that we can send, which we can't hear them, but our computers can dig them out of the noise. And let's see if I... There's probably 24 stations in that bundle of noise, and our software can pick these things out and people can have conversations. It's called FT8. And there are other digital modes where you can aim your handy-talkie, or actually add an aerial and aim it at meteor clouds, meteor traces, things of that sort. Or there are I don't know, probably about 30 satellites up in the air that you can contact other stations through. This satellite acts as a repeater. It repeats your signal down to some other area of the world. So fascinating things you can do. Or I can send Morse codes anytime I want. I'm an old-fashioned guy. I told you my Morse code story. So just about anything you want. Okay, any other questions? All right, I'm going to start with a little bit of electricity. Let's see if I can get this share screen going. Oh. Okay, everybody see this? Okay. All right, this is going to be fairly important in a little while because we're going to be talking about radio waves and do we really know what radio waves are and so on and so forth. We have to start with something like this. We're talking about movement of electrons. You know that a battery moves electrons along. And
Jerry,
yes,
we are still seeing your folder. We're not seeing the document you opened.
you're not seeing the document I opened.
No, you
Still-
when you did your
Oh,
screen
yeah,
share,
we're just
you
seeing your
shared
Windows
wrong.
Explorer.
Okay,
Yeah.
let me try it again.
Different monitor, maybe. I think we were still seeing your file folders.
He shared the
Yeah, I was
application
trying to
instead of
unmute
the
and
desktop.
let you know that.
How's that?
There we go.
Okay. there we
Awesome.
go. Okay. All right. What we're doing, we're moving electrons around in our radios. There's a magical transformation that comes about in a little that I'll explain in a little while. But anyway, a battery will move electrons in one direction through a wire, and you have a flashlight or something of that sort. Sometimes we use a Edison will use a magnet, put it through a coil of wire, and you can see the magnetic field when it goes through a wire, a copper wire or any kind of conductor, will cause electrons to flow. You can see that it flows, flashes twice for the north pole of the magnet and the south pole of the magnet. And what the electric company does is actually put the magnet inside coil of wire, and spins it. And it spins it around. You can use any kind of power to make that magnet spin. Either nuclear power, go to Niagara Falls, use the water power of the falls to make that magnet spin. And the magnet spins at 60 times per second. That's your 60 cycle alternating current electricity. And that's what you get out of the sockets of your house. Go to Europe and it's usually 220 volts. So you got to be careful. All right, now I've done lectures on radio history, and at one point, well, starting in 1906 and actually going to around World War II, there were very large alternators that were built that would spin at a higher frequency. There was one alternator, it's still there in Sweden, that spun around 17,000 cycles per second, 17,000 rotations per second. And it was used to send Morse code. The virtue of something like at that low frequency was that the signals could penetrate into the ocean, and you could signal submarines with it. And you probably heard of the ELF, the government conspiracy type thing. Well, that's what they were doing, using low frequencies to penetrate into the seawater. Anyway, this works fine up to about 100,000 revolutions per minute. But then vacuum tubes were invented, and then transistors were developed that would electronically make these electrons alternate at very, very high frequencies. Okay, I'm going to get out of this. All right, any questions so far? All right, so inside our radio, we are taking these vibrations. Let's get into okay, let's get into what should we call it? Where is the let me get out of that again. I'll hang on a second. I'll get the right one. Sorry for the delay here. I'm trying to find my other. Here. Trying to find my Kindle. Okay. Okay. You can see the vibrations here. This, and actually, when you get them high enough, they get into the radio wave area, but they're not radio waves yet. But anyway, this is a cycle. It goes from 0 to the maximum, back to 0, then the maximum and negative, back to 0. That's one cycle. And before they were called hertz, they were called cycles, kilocycles, megacycles, and so on and so forth. You can see that you can multiply these, or a multiple is called a harmonic. Like here's 1, 2.5, here's 3. This is the second harmonic. Here's 6, here's third harmonic, and so on and so forth. And hams started calling their kids harmonics. Okay. So okay, so one of the questions, what is the unit of frequency? It is well, it's called a hertz, but it's actually a cycle. T4. Okay. Hang on. What describes the number of times per second an alternating current makes a complete cycle? That is frequency. Okay. Anyway, what I'm talking about there is the way that the electrons move in so at a various frequencies. They don't become radio waves until they hit an antenna, and the antenna turns it into an electromagnetic wave. You saw the electromagnet moving electrons. You saw the magnet in the coil moving electrons, and goes the opposite direction too. I can explain that a little later on when we get into some of the principles. But anyway, when the magnetic wave goes off into space and hits another antenna, the antenna will change it back into movement of electrons, and our radios will be able to detect those and process those. So that's what we're doing. You're shooting electrons all over the place and turning them into electromagnetic waves. Okay, everyone follow?
Yeah. Hey, Jerry, quick question. The radio wave, right? After it leaves your antenna and it goes through space and time and hits another antenna.
Yes.
Is that still electrons moving through the air?
No, it's a wave. I'm not sure what it is. Well, it's back in the 1860s, scientists found that electricity and magnetism followed the same rules in behavior. And James.
Okay, so it's magnetism, electromagnetism. It's not electrons until the other side receives it and turns it back into electrons to go through the wires.
Right.
Okay.
Although no, current flowing through a coil creates the magnetic field. Magnetic fields can be transferred to another, the magnetic field can be can be induced into another coil and turned back into electronic flow.
Okay, thank you.
Okay. All right, let's get back to. Okay, next. Okay. Anyway, that's one of the, well, it's all here in the manual. One of the things they talk about, as I say, radio waves begins at an antenna, turns electrical signal into radio waves that travel at the speed of light. As the wave passes other antennas, creates replicas of usual electrical signal and turns it back into voice, digital medium, or even Morse code. All right. One of the things you're going to have to get familiar with is the international system of units. You're going to have some questions that we're going to go into mega, kilo, mostly milli, micro, and pico. Those are the ones that are usually the most used. And they're showing the multiplication factors. For instance, a mega is 1 million of something, and a pico is a 1 millionth. No, sorry, a micro is 1 millionth of something. Pico is a 1 millionth of a millionth, as you can see here. There are some parts, like a capacitor, where the unit is so huge, the farad is so huge that we do use parts that are rated at picofarads. I have a couple of capacitors in my antenna tuner, which are 500 picofarads each. Okay, so how many milliampere? A milliampere is 1/1000th. So 1.5 amperes equals 1500 milliamperes. These are questions that usually can figure out on a piece of paper or in your head. You don't have to bring a fancy calculator with you for this. But these are the questions that you will see. I don't know if Bob mentioned that all of the questions are in the back of the manual, every one of them. Now, if you're a good study, if you want to study the answers to all the questions, photographic memory, it's allowed. If you memorize all the questions, we actually figure that this is an entry. Passing the exam is an entry. You're still not a ham yet until you've really got your feet wet, until you've got some experience. What is it? What was that old TV show where the master called the novice, oh yes, grasshopper.
Kung Fu.
Kung Fu, right.
Yes.
Karate
Exactly.
Kid,
Right.
the Karate Kid.
Yeah.
Oh, that's right. That's what it was. That's right. I had the
Mr.
right
Miyagi.
genre.
Mr. Miyagi and Danielson.
Yeah. Right. And actually, the masters are here, or the helpers are called Elmers. And so at this point, we will be your Elmers and try to help you along, pass the exam, and any other questions you have, from installing a station to what kind of radio should I buy? And we advise you not to buy anything until you've had a few of these classes under your belt, and have somebody with you when you go to a swap, because there's some stuff worth buying and some stuff not. Okay, I'm going to get out of this. And
So you're saying I shouldn't already have an IC705 sitting in a box?
that's
kidding.
right. You
I'm
naughty
kidding. I'm
boy.
kidding.
You naughty boy.
I'm kidding.
Yes. Okay. All right. Okay. Okay, sure again. Okay, everybody see that?
Yep.
Okay. No, this is a canned piece. We can well, we'll go through it, and anyone have questions, we can go beyond it. Okay. Vocabulary, we went through a little bit. Here's one cycle. This is called a fundamental frequency. A multiple of that frequency, if it's doubled, it's a second harmonic. If it's tripled, it's a third harmonic. We had some circuits way back when that would multiply by 5 or 6 times to get to the frequency you wanted. Technology has changed quite a bit since that time. All right, amplitude is the, I'll call it the volume or the level at which it goes. You can increase the amplitude, go up even higher or lower. The frequency is the number of times these cycles occur per second. We use hertz or capital H, small z, as the unit. Hertz, well, using hertzes instead of cycles came in around 1960s, where someone decided that we should honor all the old inventors. Henrik Hertz actually proved that the theory of electromagnetic waves, and after his work, various inventors started building radios. Not good radios, but radios. Okay. A period, I've looked, there's no question about that, but that's number of seconds that it takes for a cycle to occur, or part of a second. Right, fundamental we saw, and the harmonics, our kids. Electric and magnetic energy fields. Now it's kind of hard to visualize. The electric field is supposed to be vertical, and the magnetic field is supposed to be horizontal as it goes. And they vary in the pattern of a sine wave. Now, if you look at, you've probably seen an oscilloscope. If not, I can hook one up for you a little later on that will show your voice. The microphone will turn your voice into electrical waves, and you'll see that they're sine waves, and they travel at the speed of light. Now, what we use for the speed of light is 300 million meters per second. Comes to 186,000 miles per second, but 300 million. We use the 300 as for our equations to figure out frequency and wavelength. Okay. When I showed you that moving magnet, now ARL is saying the moving electrons in an antenna take the place of the moving magnet. So when the magnetic field, electromagnetic field hits the antenna, turns into motion of electrons. Signal from the transmitter make the electrons in an antenna move, transferring the energy from the signal to electromagnetic waves. The antenna is a magic thing. And once I asked a question before I knew any better. Now, does the antenna wear out? You have all this activity, all this stuff coming out of the antenna, and no, it doesn't. It works backwards too. Waves encountering antenna make electrons move in sync with the wave. Energy is transferred from the wave to the electrons and down into your radio to be analyzed. Now, later on, we'll get into actually making signals. All right. Okay. It's a way of showing how to make a signal, how to make radio waves communicate. For instance, you can pretend this is a radio transmitter, and when you turn it on, it's just going to sit there. You can communicate by turning it on and off. And that's what we did for quite a while, until someone managed to connect a voice signal to the radio signal. And actually, if you turn to your AM radio, they're using that particular technology still. Now, I'd like to talk about a 16-foot long radio dial. Most of the current radios that you're going to buy, the HF radios, have receivers that will go all the way down to 30 kilohertz, and which is very, very low, and go all the way up to well, the one I have, the ICOM, goes up to 54 megahertz, which is 54 million cycles or thereabouts. And of course, when you get into higher frequencies, the drones are operating at around 2400 megahertz, which actually electronic ovens and police radars also work at around that frequency. And I belong to a group called the Old Crows, that's electromagnetic warfare, and they're doing things in the 5 to 10 gigahertz. You'll take a look at that chart again and find out about the gigas and all that. And amateurs have frequency assignments where we can operate from what is it, 37 kilohertz and all the way up to practically the light spectrum. Each range of these frequencies in the spectrum have a different name. They're called radio waves. And actually, light is a form of an electromagnetic wave, even though we can do things with lenses and things and glass that we can't do with lower frequency radio waves. So here we are, very low frequency. One thing that people might think about, it goes from 3 kilohertz to 30 kilohertz, and someone with a good high fidelity system can say, hey, 3 kilohertz, that's within hearing range. Actually, 30 kilohertz, you got cats and mice and probably dogs listening there, but they're listening to sound waves. They aren't listening to radio waves, because the sound going through a loudspeaker or through a whistle is not the same as going through an antenna. Low frequency isn't used as much anymore. If you have one of those remote set watches or clocks, there's a station that operates, I think it's around 60 kilohertz, that sets those clocks. There are navigation beacons, and in some European countries, there were even some broadcast stations that were operating down here. Once you get up to 530 kilohertz to 1500 kilohertz, that's the US AM broadcast band. And then you start right around 1.8 kilohertz to 2 kilohertz. We have a ham radio band. Right, HF is 3 megahertz to 30 megahertz. There will be a question on the exam for that. And this is where we have a lot of fun. You have limited, as a technician, you have limited privileges there. But, well, mostly using code. but well, I'll tell you when we get up to 10 meters. But we have 3.5 to 4, 5 to 5.3, 7 to 7.3 megahertz, 10 to 10.1 to 10.15 megahertz. That's code only. You have the 20 meter band, which is the most exciting one that goes worldwide almost all the time. And that's 14 to 14.350. Also 18.068 to 18.168, 21, 24 megahertz, 28 megahertz. And that's our shortwave band, the HF band. Hams gets into the VHF band. Technicians have privileges on 50 megahertz, then 144 to 148, 220 to 230, 4, and after that, you hear 88.2, 108. You have FM radio. VHF TV, I think, has moved a bit. It's gone digital, which is good for us because the 6 meter ham band used to interfere with television reception and gave us a bad name. In the UHF, you get mobile phone service, you have police radios and things of that sort, and also several amateur radio bands. Most popular is 440 to 450 megahertz. Then let's see, 902, and I think there's 1200 and 2450, I think, thereabouts. And after that, there's 3.7 to 5.7. And when we get into the EHF, I think anything over 250 gigahertz, you can do anything you want. Anyway, that's how that works. Any questions? Okay, like I say, it's a 16-foot radio dial.
Hey, Jerry, I have a stupid question. Can you back up one? And this, again, I apologize, people, if I'm asking too many questions, tell me to shut up. But the part where the HF spectrum lies, the bands, right? So the 10 or 20 meter, that's called shortwave. Yet that's on the long wavelengths half of the spectrum. So wouldn't that be called long wave? Why is that called shortwave?
Well, it's like this. When these things were first put together, we're talking about the 19 teens.
Mm-hmm.
There was a actually it was about 1912, I think it was, where hams were first regulated. They had to have a license, and they could, before that, they could use anything they wanted, any frequency they wanted. They were interfering with a government station, with naval ships and things of that sort. The Federal Radio Commission that was created said, let's put the hams on the useless frequencies. Nobody ever makes contacts up above, I think it was 1.5 megahertz. So let's put them all up there. What they didn't know was that the radio waves in the shortwave band and the HF band would start bouncing across the ionosphere and giving much better communications. Most of the commercial communications were down in the very low frequency and low frequency bands.
Okay, so it's a product of how this all came about many years ago. Thank you.
Yes, yes. Okay, anything else? Okay. Parts of the bands: AM band, CB band. Okay, usually the same kinds, you're going in the AM broadcast band. These are all going to be the same kind of signal. And that's good because well, car manufacturers want their radios to be consistent. We show the band across many signals of different types. Okay, this is a kind of cross section of the AM radio band. These are different stations. You can see the higher amplitude. In between, there's noise. And as you tune the dial, well, I mean, it's digitally done now, but with the old radio, you tune the dial and you'd tune across the signal to the best reception that you can get. Something you're going to find off little prediction. You'll find that if you listen during the day, you're going to hear many fewer stations than at night. And I know I think Bob had a little excitement when he first started by listening. I know I did by listening to stations from Detroit to Waterloo, Iowa, places like that. Okay. A radio wave carrying information is a radio signal. Each signal occupies a range of frequencies. Now, instead of just a single line with that one frequency, that's that one just sitting there, not doing anything but taking space. You mix the audio or music with that, and you have takes a little more space. Okay, receivers tune into a signal by listening at the signal's frequency. Wavelength. All right, you're going to be confused a little bit by wavelength versus frequency. There is a formula we have. The wavelength is the actual length of the radio wave. The distance of one complete cycle. And for a long time during radio history, that is how people measured where a radio station was in the frequency spectrum. Wavelength, the formula down here, is speed of light divided by the frequency in megahertz. All right, so easiest thing I can an example would be we have what's called the 6 meter band. How does it become the 6 meter band? Wavelength 300 divided by 50 megahertz equals 6. The 2 meter band, it's not a very exact, but it's close. But 150 megahertz. So 300 divided by 150 megahertz equals 2 meter band. And if you want to go down to say the 10 meter band, which is in the HF spectrum, that's 300 divided by 30 is 10. So that's the 30 megahertz equals 10 meters. we use lambda as the symbol for wavelength. So sometimes you'll see an antenna that has lambda divided by 2, means the length is the wavelength divided by 2. And again, they repeat, waves travel at the speed of light. Now, speed of light, we're talking here using the 300 figure as the speed of light in a vacuum. If it goes through other kinds of medium, like through water or through certain kinds of cables that go out of between the transmitter and the antenna, then sometimes it goes a bit slower. Okay, so here's what I said, it's 50 megahertz, 6 meters. Okay, some questions.
Yeah, I have a quick question about that AM
Yes.
AM frequency chart. I think it was 2 slides ago where it showed the
Yes,
so you mentioned that the width of that. So, you know, if I'm looking at the 800 kilohertz, it's obviously 800's the dead center. What determines how wide that is? Is it the quality of the audio, like the bit rate? What determines how wide that is off of the set given frequency?
all right, what we're doing is mixing 2 frequencies. So we are mixing audio with the fundamental frequency. So for instance, at 800 kilohertz, 800 kilohertz signal, what is that, CKLW in the
Yeah.
Detroit area. All right, if you're talking, if you're using voice, I don't know, I guess they'd go up to around 3 or 4 kilohertz or thereabouts. So it would be, the width would be 800 plus the 3 kilohertz. So 803 and 797 thereabouts. That would determine the width. If you're playing music, it's going to be a bit wider because music has goes to a higher frequency or a lower frequency.
So Jerry, does that mean that at 800 kilohertz, just 800 would just be an 800 kilohertz tone, where when
Yes.
we have it broader, now we can have the actual voice, which is little bit changing tone?
Exactly.
Okay, I get it. That was a
Okay.
good question.
Yeah, that what you just said really helped make sense to me. Thank you.
Okay, and our ham equipment is a little more sophisticated because it gets rid of the carrier signal and it gets rid of one of the side, call it side bands, and so it makes it concentrates our power into a much narrower bit of the spectrum. It gets farther.
So more efficiency.
Yes.
Yep. Okay.
I participated in the single sideband wars, they called it, because with a regular AM receiver, single sideband is going to cool, very muffled, very you have to put a special circuit in to be able to listen to it, and it was very bitter, but single sideband actually won after a while. Okay. Distance, a radio wave travels one complete cycle. We can all answer in unison or whatever.
That's
Wavelength.
the frequency.
Wavelength, the distance,
Yeah,
that's the length.
yeah, wavelength. That is a wavelength.
Okay. How fast through free space?
Speed of light,
300.
300
light.
me. Yeah.
300 million. Okay. Wavelength relate to the frequency. Wavelength equals,
The speed of light divided by the frequency.
yep, you got it. And as a corollary, the wavelength gets shorter as the frequency increases. So when I'm at 80 meters, the frequency is actually somewhere around 3.5 megahertz. If I'm at 2 meters, we're talking 144 to 148 megahertz. So the wavelength is shorter. And when we get to 440 megahertz, we call it the 77 centimeter band because the wavelength has reduced down more and more. Actually, after 440 or 70 centimeters, we just talk about megahertz. We don't talk about the wavelength anymore. It just gets too short. Frequency to wavelength in meters. Okay. Frequency equals. Do a little
Frequency
algebraic.
equals the it's either speed of light divided by
Frequency in megahertz. Yep.
Yep. Yeah. Just a simple substitution.
I couldn't remember if it was which way it went was my problem.
Okay. Yeah, I have a bunch of 10-year-old kids that I'm teaching some electricity to. I'd love to get them into the studying for their ham licenses, but they just don't have the math yet. They're starting long division. So another year or so, and they'll be able to solve these simple questions. Property of radio waves often to identify the different frequency bands.
The wavelength.
Yep. And you see that ARRL is hedging their bets, the approximate wavelength. Because 150 megahertz is not really the 2 meter hand band. Frequency limits of the VHF spectrum. Now we had that little chart, 30 to 300, 300 to
It's 30 to 3. The answer is 30 to 300 meters.
3 to 300, and for UHF it's 300 to 3,000. UHF spectrum. That's okay. So you can look up the various sections. If you go to the last chapter in the book, there's a little chart that tells you what questions they're asking. Each question has a certain designation, and some are relegated to different rules and regulations. Others are to parts and parts of circuits. Others to wavelength. Frequency range referred to as HF. HF, anybody?
This is one of the ones I never get right on this exam.
3 to 30.
You got it. All right, so some of the stuff, you can logic out, and some of the stuff you're just going to have to pound it in. Okay. We already had that 300 million meters per second. And it is easier to figure out things by lopping off a bunch of zeros. Unit of frequency.
Hertz.
Yeah, Heinrich Hertz, brilliant guy who died too young.
Radio frequency of all types.
What?
Radio frequency of all types.
Signals of all types, yeah. And yeah, we talk about RF energy, radio frequency energy. And if you touch an antenna when the transmitter is on, you're going to get a dose of RF energy, which is not good. Probably won't shock you to death, but it does create burns that heal very slowly. Speak from experience there. Okay, I'm going to stop share get out of this.
That would actually be some sort of, I mean, it's technically a type of radiation, so that'd be some sort of radiation burn, wouldn't it? Or is it just
Well,
heat? Is it just the heat from the, is it just the heat from the coil and the antenna heating up?
It's
no,
a radio
it's-
frequency burn.
It's right. It's radiation, but it's not the bad radiation like
Yeah, it's
gamma rays.
non-ionizing.
No,
Yeah,
no,
yeah.
It's not. No, what we have is non-ionizing, but there's enough concern that when we get into the safety chapter, we're going to be talking about how far an antenna should be from the general public, and so on and so forth. As a matter of fact, I should worry a little bit because I've got an antenna in the attic, which let's see, where am I? I have an antenna in the attic, which is about 7 or 8 feet away from me. And not sure whether I'm not sure whether I should either, well, I don't want to move it, but I could possibly lower the power and the exposure, but I don't use that antenna very much anymore. All right, modulation and bandwidth. Can everybody see this?
Yes. Yeah.
Okay. All right. First of all, this is pretty much what we have. This is all nowadays is built into one box. Right. I'm going to let's see. The idea was kind of revolutionary for its time, but if you take a look at my little box, you'll see a guy who is operating. This is probably 1946. He's operating. It's called a T19 Mark II transmitter receiver. It was built for World War II, and it was a transceiver. It had a transmitter and receiver that were linked to the same frequency. In the olden days, we'd have separate boxes. Sometimes, well, as a technician, I could not a technician, as a novice, I could only use crystals, which put my frequency at a fixed place unless I changed crystals. So I would call CQ, and then I would tune around 15 or 30 kilohertz away from my sending frequency to see if anyone answered. So this radio was very nice for its time. One interesting thing about it was that it was the labels were in English and Russian. It was supposed to be Lend-Lease to be given to the Russian government while they were fighting off the Nazis. Okay, let's see. All right. So anyway, there was a switch that will switch from the transmitter to the receiver. And so you had a single antenna and a feed line, since the antennas were usually quite a ways away. For instance, my antennas are probably about 40 feet away. So I have 40 plus about 30 feet straight vertical of feed line of cables that go up to the antennas. All right, what happens during radio communication? You transmit, And we will show you, we'll have examples of radio communications, of talking, because a lot of people will freeze up. Oh, what am I supposed to say? So don't have to worry about that. We'll help you. Okay. Information, voice data, video commands converted into an electronic form. The microphone has some kind of an element, crystal, ceramic, or various other things that will change the sound waves into electrical waves, or not electrical waves, into electrical or electron movement, I guess you'd call it. And voice is pretty much alternating current, or alternating, so it's like a sine wave. All right, the information in electronic form is added to a radio wave, as I was describing the AM radio. Okay, radio wave carrying the information is sent from the station antenna into space. Receiving, you have your catcher's mitt out, and your receiving station is going to, station's antenna is going to pick up the electromagnetic wave, extracts the information, and present it in a way that it could be understood. I have some software that will send, it's called Slow Scan TV. It'll send pictures on the 20 meter band. Words on a computer. We can play with that when I put my station on the air. Response to a command. In other words, turn off the satellite, turn off your transmitter on such and such frequency, and things of that sort. It can be simple or complex. Over the last 20, 30 years, it's gotten very complex. You need computers to do all the work for you. And it's wonderful. As I say, I've been in the hobby long enough, so I know the old-fashioned way, and it's more enjoyable this way, even though some guys will complain. Okay. Going to be required only to know the basics. As I say, the information is a mile wide, but an inch deep. And this will get you into the tent, and then you pick up as much as you want. Some people will just stay. They just want to talk to the guys on Sunday, or talk to them in the car while they're on their way to the restaurant for the club breakfast. But it's I think the Ann Arbor Radio Club calls it an egg chew. Okay. Questions so far? All right. You know what? Okay, good. And okay. Let's Joe. Okay. Oh, Hugh, are you here?
I am.
Great.
Hang on, let me turn the volume up. I got a late start tonight.
Okay.
All right. I was just doing my check-in at Oakland County ARSPC.
Okay. Hugh is another member of our team. He usually does the technical type of stuff. He's got a lot of good show and tell. He's got kits that he's made, and he's the one who's a curvature of the earth prevents him from checking into our nets from where he is. Where are you now? Are you in town?
We just got in town, probably about 6:30. That's why I was a little tardy tonight. I apologize.
Oh, okay. But anyway, he's about 3 miles from the repeater. So now curvature of the earth doesn't hide him. Okay. All right. I think most of you are within range of a good repeater. Let's see. I think who's our Connecticut man? Okay, Hal. Hal, you there?
Yes, I'm here. Sorry, I was just unmuting. Yeah, a friend of mine is a ham radio aficionado, and he says there's plenty of repeaters here.
Okay, whereabouts in Connecticut are you?
I'm actually 8.3 miles according to Google from ARRL.
Definitely. And you will have a chance to operate at the sacred radio station there. They have one that's open to people.
That would be a lot of fun.
It will be. They've got some state-of-the-art stuff there, as well as some old-fashioned stuff. So you'll that's great. I'm glad. I'm very glad for you. Okay.
Thank you for doing this class.
A pleasure. Okay. All right, we're adding some information to the radio wave carrier. We modulate the wave. First instance of that was a fellow died, I think it was 1904. He had one of those alternator motors revved up, and he managed to induce the microphone was so hot they had to cool it with a water hose going through it. Anyway, he had to he transmitted, he played the violin, read something from the Bible. This was on Christmas Eve, and ships at sea who had never heard this stuff before were very, very surprised. But it was the first instance. There weren't any other radio stations, not until 1920 that KDKA in Pennsylvania started the first regular broadcast. But anyway, it was the first audio type, and he, I think he called, what was that called, impressing the two signals? He called it heterodyning, mixing two signals together, the audio plus the carrier. Excuse me a second. Okay. Okay. All right. Adding information to the wave, Morse code. And it's still used quite a bit. Gets out farther, you can talk with your mouth shut. All right. Speech or music, you can add that. No music on ham radio bands. I think there's one exception. I think when they wake the ISS astronauts up in the morning. Data. You can. There are ways of mixing amplitude and frequency modulating the signal to make the digital signals. Okay. All right, there are amplitude, frequency, or phase. Frequency or phase modulation are pretty much the same thing, but amplitude modulation is making the signal level go up and down according to the modulation that you're adding. Phase. All right. Some of you may, if you're into electricity, you may know about 2 and 3 phase power and such. For instance, these two signals here are 90 degrees out of phase. Right, phase is any place along here that you can study. This is 180 degrees out of phase and could possibly cancel each other out. It's the position within a cycle. Here, 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 here. And the relative position between two waves, as I mentioned. Okay, C.W. Morse. If you ever get a hold of a copy of QST magazine, you'll see when they review radio transmitters, they will show how fast the signal turns on and turns off. Right, using a key, use dot, dash, dits and das. This is a dit and that's a da. The da is supposed to be 3 times as long as a dit. If you want to learn Morse code, there are some really good programs that you can download for free. And I'll give you a command of it. And to me, it's, well, it's been worked well. I started with it and I still use it a lot. Amplitude modulation, the carrier wave, the audio
Quick
wave.
question.
Yes,
Quick question for you, Jerry, on Morse code.
yes.
Is it internationally? I mean, obviously there's hundreds of different languages throughout the world. When you communicate to other countries in other in Morse code, is it universally English? What alphabet? Or are there different Morse code alphabets in different languages?
Well, last question first. Yes, there are different Morse codes in different languages. For instance, there's a symbol for the ha sound for German, for instance. But most hams will either know English or know enough English to get by, or they will use universally accepted abbreviations or signals. A little later on, I think Mike will get into this. We have certain signals like QRZ or QRS or QRM, which mean certain things. Like QRM means I'm being interfered with, or are you being interfered with? And QR Nancy is are you being played with static, or I'm being played with static, things like that. But you'll be able to make many good Morse code or English conversations with other hams.
Gotcha. Thank you.
Sure. Okay. Composite signals. All right. Sidebands. Okay. Let's see. I'm looking for here it is. Here it is. Okay. All right. All right. CKLW is in Windsor, Canada, has a carrier, and when the guy's talking, the sidebands are going to vary up and down according to the voice or music that's being carried. Each of these intervals between the carrier and the sideband are identical. So that's why you can electronically get rid of one of the sidebands and still have all the information. And if you can filter out the carrier, then all you have is this little bit of frequency that's being used. This is not new technology. It's it was used back in the 1920s on telephone lines. Okay, this, as you see, this is we're using a 600 tone hertz tone. So you have 800 to 800.6 or 799.4 to 800. So that's the bandwidth. Lower sideband, upper sideband. And when we get into operating characteristics, certain frequencies, our radios use lower sideband. Other frequencies, we use upper sideband. For aircraft and government work, it's always upper sideband. All right, AM bandwidth, twice the information bandwidth. As I said, each of these sidebands is duplicate. Voice information. And here's the guy singing or the music playing or whatever. It varies and varies and varies. All right, according
Is the information to the lower and upper identical, or are they unique?
they're mirror image, they're identical.
Okay.
And the way the channels are set up in on AM broadcasting, 3,000 hertz wide. So the entire signal will take 1,200 hertz. Oh, sorry, 12,000 or 12 kilohertz. And
Gotcha. Thank you.
Yeah, that's a lot of bandwidth. Considering when we hams start transmitting on single sideband, our bandwidth is something like up to 2.5 or 2,500 hertz. Period. So AM voice is I correct myself, 6,000 hertz for a versus 2,500 hertz for hams with single sideband. So you can filter out the suppressed carrier. I mean, okay, I got a question. I know that there are two people who are awake because they're asking me questions. Is everybody else around? Are you still conscious?
Yep. It's just a lot of information trying to process it.
Yeah, exactly. Okay, well, you can see a repeat of this. I'll refer you to a couple of places on the internet, on YouTube, where you can get second opinions or some supplemental information. Like Ham 2.0 is an excellent place. Bob, I'll ask you to possibly forward some of this information to people, and you can get, as I say, a second opinion or supplemental types of information. Okay, so as I was saying, we're having electronically getting rid of one complete sideband and the carrier, because the carrier really isn't doing anything. And electronically, we can reconstruct the missing carrier. And once we have the reconstructed carrier, the sideband will bounce against it, and there you have your signal. Phase modulation is different. Now, frequency and phase modulation. Instead of making the signal go up and down in volume or amplitude, the amplitude is the same, stays the same. However, you wiggle the frequency according to the modulation. You start adding this carrier, it's adding the voice or music, and you can see the frequency wiggle. And it's that wiggling that the receiver picks up and changes back into the signal that you want to listen to. It's the I don't know why they called it. This is stuff that was done during the late 1920s, early 1930s, but they called the circuit a discriminator circuit. I guess it could discriminate the frequency changes. So an FM or phase modulated signal is going to be quite a bit broader than an AM signal.
Excuse me, Jerry, is frequency modulation and phase modulation the same thing or different things?
Depends on where what stage of the radio circuit the change in frequency is made.
Okay.
So it's not really that big a deal. All right. FM bandwidth for voice is between 5 and 15 kilohertz. So you could usually it's 15 kilohertz for 12 kilohertz, isn't it, Bob, for our analog FM signals? Okay. And when you get into FM broadcast stations, we're talking possibly upwards of 100 kilohertz. That's why FM has much nicer fidelity for good music. Okay, shift the phase back and forth. That's the point at which the point at which where the signal falls. I think we saw phase modulations. We're showing a sine wave, and instead of picking up the peaks, you can go to different parts of the signal. So it's very similar to FM. And actually, I can't tell these radios, the Baofeng and got my little Yaesu here. They're doesn't really matter. Radios can pick those out. It doesn't really matter whether it's phase modulated or frequency modulated. It's as I say, it depends on where the wibble wobble is introduced into the circuitry. Okay. So, all right, these are things that they're going to talk about on the exam. AM voice, broadcast 10. Commercial video broadcast, they didn't talk about very much. Things are sort of up and down, up in the air right now because the video broadcasts are now digital. So we don't have the same kind of game anymore. So single sideband voice, single sideband digital, you'll find that the digital signals that we'll encounter, you will have your radio set to usually upper sideband or lower sideband. You can see that CW, just turning a carrier on and off, is the narrowest, 150 hertz or 0.15 kilohertz. FM voice, 10 to 15 kilohertz. FM broadcast, 150 kilohertz. Now, one of the things that we do with the amateur radio service is that we try to narrow in the frequency range that we use. So our microphones and such are usually going to be centered on 300 hertz up to about 3000 hertz. So you're not going to get ultimate high fidelity out of that. But that's the voice range. The studies were made, especially during World War II, the voice range that's is most intelligible and carries the most information. Okay, any questions on that?
Nope.
Okay, so you probably heard people talking on the telephone on being broadcast. You know how narrow that is. It's because the telephone company is also trying to maximize the intelligibility. They don't care about the music. Okay. Why should you not set your transmit frequency at exactly the edge of an amateur band or subband? For instance, the lower limit of an amateur radio band for 40 meters is 7.000 megahertz. If you put your transmit frequency on 7.000, what's going to happen when you transmit?
Your lower
your lower, yeah, exactly. Yeah, you had it. Lower sideband's going to bleed into the lower range.
Right. And you're off frequency and you're in trouble. We do a lot of self-regulations. There are official observers. I think they changed the nomenclature, but they'll send you a friendly postcard or email. But if the FCC sees that you're doing stuff, or if someone notifies the FCC, they will investigate. The wheels of the FCC grind slowly, but they grind exceedingly fine too.
Jerry, what's the consequence, if I may ask, of failing to comply with the ham radio rules? I mean, beyond, I assume you can get your license revoked, but are there other, in general, penalties for making mistakes?
License revoked, your equipment confiscated. There are monetary fines. I did see some reference to 10,000 basic plus 1,000 per day that you violated. And
I can share a brief story about that. When I was very young, I'm 44 years old right now, by the way. So I'm talking, I was 10 or 11. My father had a boat and it was sitting in our driveway and we were winterizing it. And I hopped on the marine radio and started talking to people. And like a dumb kid, my dad and I always went fishing. So I knew where the good fishing spots were. So I was telling people where the fishing spots were. And someone who turned out to be, I think, the Coast Guard or an observer, like you mentioned, hopped on and started talking to me and started offering me money for my fishing tips and asked where they could send them. And again, a dumb kid, I told him where I lived. And sure enough, a couple months later, my dad got a visit from someone. And yeah, that was a scary experience being a little kid. So they will find you and they will do something about it.
But now I have to ask Clayton if your dad was more mad that you got in trouble with the FCC or that you told about his good fishing spots.
I think both, to be honest with you. Yeah. I was not allowed in the boat anymore by myself. I will tell you that.
all right. Yes. Well, one of the questions I'll put to you later on. All right. A fellow contacted me. He said that his brother was in North Korea on business, and he had to get some prices for some things. I think there were capacitors that were used in nuclear bombs or something of that sort. And he needed the pricing information real quick. Would I contact someone in North Korea and give him the prices? And of course, my question is, how many rules am I violating by saying yes? And we'll go over some of those rules too.
I don't think North Korea is on the friendly list with
That's one of them.
yeah.
That's one of them. It goes on.
I'm sure there's some tariffs and import laws and stuff there too.
Can't make money either, right?
Right. Yeah, right.
Yeah.
Can't take money. And yeah, and who would want to sell North Korea's atomic parts?
Mhm.
And I think you're only allowed to sell amateur radio equipment as long as it's not part of regular, like gets your primary income. So it's like a one-time thing or one-off things.
Well, usually if you go on the Sunday nets, Bob will tell you, one of your questions, Bob, is there anyone have anything to sell? And I think you mentioned the requirements as far as what they can sell and so on. Okay. All right. Oh, okay. We have another couple of answers here. Calibration error in the transmitter frequency display. They're a heck of a lot more accurate than they used to be. I have a what's called a crystal calibrator that's sends signals spaced 100 kilohertz or 100 kilohertz apart, so you could change, sort of adjust the error of your radio. And even though these are much more accurate, they can be off a little bit. Calibration error, modulation sidebands, that was the first answer we got. And to allow for transmitter frequency drift. They don't drift nearly as much as they used to, but it's possible. Okay, what determines the amount of deviation of an FM as opposed to a PM signal? Amplitude of the modulating signal. Okay. There is no question about phase modulation in the exam. I looked. What happens when the deviation of an FM transmitter is increased?
The impedance decreases. Or no, the signal.
It occupies more bandwidth. Now you're going to find with the exams, and I'll probably harp on this a lot. There are 4 answers. 2 of the answers are just bat crazy, so you can throw them away. So now you have a 50% chance. And if you're taking the exam and you don't know the answer, guess. You still have a chance. What's a form of amplitude modulation? Okay, signal sideband is. All right, VHF packet radio transmissions. We haven't gotten into that yet. And so they're sending a bunch of tones and things. And that's on VHF, we usually use FM. That's a convention. The only time we use amplitude modulation would be either CW or single sideband. Use it for long distance types of adventures.
Is the reason VHF is used or FM is used because the fidelity of FM is better, so the quality of the tones is cleaner? Is that a reasonable reason?
Not really. It's more that the higher wavelength bands are bigger, or you can fit more signals on.
Okay.
So you have that much more territory, and also, the limited range of this. FM has a quality. It's called capture. So you have 2 interfering stations. If you're listening to if you're listening and 2 stations answer you, the stronger signal, the stronger station is going to capture the frequency, and you'll hear him. You won't hear the other guy. All right,
So
so what,
wait, so Jerry, let me ask about that, please, quickly. If we have two transmitters transmitting on the identical frequency, and one of them is significantly more powerful or more powerful and closer, I'm not going to get a mix of both. I will only receive the stronger one, or I guess in this case, maybe the closer one too. Is that correct?
yes.
Oh, okay, cool. Didn't know that. Thanks.
Um,
And is that a product of the circuitry in the radio filtering out the weaker one, or is that just the way the radio waves come across?
It's pretty much the way the discriminator works.
Okay.
Okay, let's see if I can. It's a little late. I'm looking for. No, I can't find a pile up. But if I come across it, I have my HF radio on, and sometimes a rare station will come on, and hundreds of people will try calling them, and I'll see if I can get a recording of a pile up so you can hear how it sounds. Okay, long distance or weak signal contacts in the VHF, UHF bands, as I mentioned, sideband. And actually, you're going to find that the FM radios are going to use antennas that are up and down vertically polarized. And the single sidebands and CW signals are going to use horizontal. The antennas are going to be flat horizontal, like a TV antenna. Okay, type of modulation, voice repeaters, as I just said, FM. All right, sideband used for 10 meter HF, VHF, UHF, single sidebands communications.
Upper.
Upper, yes. And like I say, government work. Single sideband over FM.
It's it's more likely to propagate through the ionosphere. Narrow band.
Narrower. So about up to 2.5 or 3 kilohertz versus up to 12 kilohertz bandwidth. Bandwidth, VHF, repeater, FM, phone signal. These are all things that you're going to have to look up, do your questions. All right, this is all stuff that you're not getting yet. All right, we'll worry about that later. Okay, I'm going to get out of that. Now, hope I haven't bored you too much. I mean, I've had a couple of good questions come through. I'm really happy about that. Now, anyone have any other questions before we start closing it down?
I have a quick one on practice tests. I have
Yes.
an app on my phone. I have an app on my phone that I've been using along with the book, and I believe it's called Ham Test Prep, and its icon is the ARRL logo. Is that something? Is that a good one you guys recognize or recommend? It seems to downloads updated questions and keeps your statistics as you kind of learn the pool of questions. Is that a good one?
That's a good one.
Okay.
Clayton, could you repeat what that one was again, please?
Yeah, in the I'm an Android guy, so in the App Store it is called
Ham
let
test
me make
prep.
sure. Exactly. Yeah,
I
and
guess
it's
that's
I
pretty
use-
self-explanatory. All right, thanks.
I use the exact same app. I'm at getting like 80 to 90% in all my tests right now.
Guys are
yeah, I'm pretty
too far
close.
ahead.
I'm pretty close to that. Yeah. It's like a
And-
little square with the yellow triangle with the same logo that's on our book.
It's going to be
And
a
there's a
blue, white
Go ahead.
background to the square.
Yeah, and there's 2 versions in the app, at least in the Android store. I think they
That's
call
where-
one,
This is
Yeah,
Roy Watson's test. No, I have ham radio exam that I've been using. But anyway, that's good. I think if you take the trouble to do the ARRL website, I think it's a little more sophisticated where you can dictate the style of questions and all that. And actually, if you're getting more than 85%, then you're ready to take the exam. The thing is, you'll have the license, but you won't know how to be a ham yet. That's the big thing. And we are finding we're going to have to give a lot more encouragement, but we are finding a lot of people getting their licenses, and then somehow or other they fall out of love. Got to fix that.
Yes, I've already joined the club.
Great. All right, so we will see you on
Tuesday.
Wednesday.
Wednesday.
Yeah, second Wednesday of every month.
Okay. I thought I read Tuesday. I'll have to double check my schedule.
Okay, and also, after you've taken this class and or passed your exam through our exam, we will give you a 1-year free membership to the Hazel Park Amateur Radio Club. And we have remote Zoom, so you, even from Connecticut, you can still join.
All right.
So
well,
you
thank very
guys,
much.
you guys do offer the test as well. So once we've kind of finished the class and studied and can, pass the practice tests, you guys do offer the test?
We offer the test at the Oak Park Library. It's 9.5 mile and Coolidge. We're not into the electronic testing, but if you want, one of our guys is very active in that, and he can hook you up. For that, you need a computer plus a device. The device will monitor you, make sure that you're not lifting your eyeballs to see the answers tattooed there, things like that.
Speaking of that, Jerry, I understand that one can bring a calculator to the exam, but not any kind of, like, not a computer or phone. So if I use my calculator on my iPhone, for instance, I should just find my old calculator somewhere, right?
Yeah, and we got $4 or $5 dollar store calculators.
Yeah,
For the
yeah.
first-
If you show up for our test, we can loan you a calculator.
Cool.
Yeah.
You-
Yeah, these
you really-
guys, you don't need high math for this one.
No, you don't.
From what I've seen on the practice exams, you probably won't need a calculator because most of the conversions are of decimal place shifts.
Mm,
And if you just figure out what those decimal place shifts are by reading what they're asking you to convert, you'll be able to easily just move that decimal place and get the right answer.
great.
And
If that makes sense.
Bob, what are the 3 answers that you have for decibels?
What, 310 and -6?
Yes. It's
You know what? I haven't
Life
looked to
is
see if
too-
those questions are still on the new exam.
Yeah.
So,
life is too short to have to bother your head about that.
yeah,
God bless the metric system.
yeah.
It's so much
Just move,
easier.
just move the decimal point.
Right.
It's so much easier.
Okay. Anything else?
So we're
So,
back here
you know
next
what, let me
Thursday,
ask
same
what-
time.
Yeah, let me ask one quick question here. I know this time we had to do it Zoom only. If we were to hold this in person, would people show up, or do people prefer the Zoom version?
I kind of prefer Zoom, but I'm about probably an hour north. But I mean, if you could, I don't know if it's possible to do both. I mean, probably most people would like to do in person, but it's just kind of.
I was kind of thinking most people wouldn't like to do in
Oh,
person.
okay.
But
Because I like Zoom.
I live 9 in Hazel Park, 9 mile in Ferndale, like a mile from the Hazel Park Library. And I would prefer to still do it at my house since it's
Yeah.
in Southfield.
Well,
Yeah,
okay.
right.
Yeah, we'd be in Southfields if we're going to give a live course. Now
I'll vote for Zoom.
I'll vote for Zoom.
okay.
You're kind of, you're not making that hall.
Well,
That's right.
this works for me because I live up in Rochester Hills, and so there's no expressway to get to Southfield. It's all surface streets pretty much. So
Yeah, I'm over by you, Bob. Hey, quick, I'm sorry, but last thing. I heard Wednesday, but on my calendar, I downloaded the series. My next one shows the same time, same day next week, 7 p.m. Eastern on Thursday, January 12th. Is that correct?
I was
for this class,
about the
yes, for
radio
this
club.
class.
Yeah,
Yes,
I was talking
okay.
about the radio club's monthly meeting.
Oh, okay, sorry.
It's on Wednesdays. It's second Wednesday of the month at the Hazel Park Library. That's 9 Mile and John R.
Understood. Thank you. Sorry.
I joined before I realized there was a benefit to getting in for free, taking this class and passing your exam.
Oh,
It's okay.
sorry.
It's worth the
You don't
money to
have to
me.
be you don't have to be a member to come to meetings. So if while you're taking this course, if you want to come to the meetings, you're more than welcome to.
Yeah. Mhm.
Yeah, sure. We
We
want to.
encourage you to. Yes.
Actually, we have a new program now. If you need some advice from somebody, they give you a little thing to put around your neck, and the Elmers will have something around their neck, so you can identify the guys you can ask questions. I mean, no one is going to bite your head off.
So I had something, not really a question, but we were talking about the speed of light. So the faster you travel towards the speed of light, the slower time moves for you. So at 80% the speed of light, time would travel at 10 years for every 1 year. At the speed of light, time does not exist. So for a radio wave, time does not exist. So for a radio, that transmission is instant.
No, all of those assumptions, the thing has to have mass, and light and EM waves don't have mass, so it doesn't apply.
Right.
Hope none of that's going to be on the exam because I didn't
Thanks,
understand what the
Dave.
heck you guys are talking
No,
about.
the theory of relativity, the equation has m in it, right? And there is no m in this, so that's why it doesn't apply to EM waves.
Yeah, I wrote a paper on proving time travel exists in college just for the fun of it, and I learned that.
Right. Have you met yourself yet?
I have not. While time travel is theoretically possible, physically it is not.
Okay, well, we
If you want to meet yourself, just, take a schizophrenic drug, and
Yeah.
Well, I wanted to commit murder, so I went back and made sure that the guy's parents never met.
That makes it better.
Although we do use a velocity factor, as I mentioned, when we determine the length of feed lines and things of that sort of coaxial cable. So, oh my, who's that with you, Les? You're muted there.
let me.
Okay. Let's next week I will bring you a
Ria.
picture.
It's Ria, my border collie.
Okay.
Okay, next week I'll bring you a picture of Gromit. I don't know if you've seen the cartoon Wallace and Gromit, but he's a dog that he sits on a couch and he reads a book, Electronics for Dogs.
Is he going to get his ham license?
He probably could. He's smarter than his master.
Yeah, the same here.
Okay, guys, it's been a pleasure. And,
Thanks
all
again.
right,
Next week.
tell you what, email any of us if you have any questions during the week, and we can figure out something, or just tell you, I don't know. Anyway.
So I have a question. So next week, has it been assigned which chapters we're covering?
Next
yeah.
week is going to be chapter 3.
Chapter 3. Okay.
Yes.
That's Bob's going to take that propagation and antennas.
Great.
Chapter 3 is, that's you again, electricity and basics
Oh.
components. I'm
Oh.
chapter 4, propagation
okay.
antennas, which is going to be on the 19th.
Okay, that's the one regret I have of not having a live class because I have a show and tell. And I can only show you through the camera.
Yeah, but it's worked in past ones, because we haven't had a live class since COVID started. So, we've been doing this all on Zoom, and it's worked. So
Yeah, it'll work.
it'll
We
work.
appreciate the Elmers. Thanks again, gentlemen. Have a great
Okay,
night.
thanks.
Yeah,
Good night,
see
all.
you next week.
Okay, good night.